All right, let's see where we're at again. When you see this, you're going to think this is not hard. But when you got to kind of think on your feet or see it for the first time, it can be harder than maybe we think. Sine of x. Okay, that didn't work. So sine of x is what I just wrote down. So this is all the sine of x. Well, notice what we've done. If I move this over, even though I have a power of 1 and a 1 factorial, since those are really just 1s, that's really an x. So couldn't I move that over and then create sine of x minus an x? So now don't I have the first two terms on the left-hand side? Well, think about what x cubed over 3 factorial is. Couldn't I move that over to the other side by adding it? And haven't I now created what we were looking for here? So what that would then have to be equal to is whatever remains. So you would have an x to the 5th over this 5 factorial minus an x to the 7th, 7 factorial. We just basically rewrite the handful. I think I wanted the first 3. So those are our first 3. And then dot, 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 dot. Write that general term. All right. Definitely alternates. So like I've been saying, I would treat that as its own separate expression because that's easy. Then we can eliminate that from our thought process for everything else. One thing we want to know, since we're using sine of x, when we go x to the first cubed, 5, 7, 9, 11, the sine of x starts at 0. So the new one needs to still start at that 0 because we can always play little games with this. But since we're using sine of x and we're going to get the first term from an n value of 0, this has to start at n equals 0 as well. We know we're going to have an x. And then we know we're going to have something with a factorial behind it. But we just want to make sure when I plug in a 0, I get 5 for the first term. When I plug in a 1, I should get a 7 everywhere. So wouldn't that be, to make sure that we stay odd, 2n plus 5? And then if n is a 0, you get a 5. If n is a 1, you get a 7. If n is a 2, you get a 9. And then on the bottom, wouldn't it have to be then the exact same thing, 2n plus 5 factorial? All right. So good stuff there. Makes us think a little bit, which is good. Okay, the rest of that I'll leave you. Again, this is stuff. This is the most weight of any topic on the AP test. So know this review well, know this module or this chapter well, and for sure you're going to get 1 for your response question on it. So then if you're able to print it, and if not, just follow along. You can write down on a scratch piece of paper here. Just a couple more for response questions. And there's a couple that I want to see more than the others. I definitely want us to see number 1 because it's a good little review also. So again, this is not in your packet. This I just put on Canvas. So there's not a lot to write down. So if you have a blank piece, you can just write the problem out. It shouldn't take you too long to be able to do that. But pretty simple little setup for the first one. A function is defined by, then you're given the function. And notice we can use the equal sign because we're given the general term here. So that's nice. And then it's that function for all x in the interval of convergence. So letter A, just a simple little limit problem. So with any limit problem, you're going to try to substitute. So if we try to substitute in, take your 0, plug it into f of 0. Again, this is f right here. So think about what happens if f or x is a 0. Wouldn't we get f of 0? And if I found f of 0 here, I would get the 1/3. But then doesn't every term after that have an x in it? So x, x squared, x cubed, x to the 4th. So the only thing we're going to be left with is the 1/3. And then I'm going to subtract a 1/3. And then when I take or plug in that 0 into my denominator, that's obviously a 0. So doesn't that very quickly then give us a 0 over a 0? And then that right away is L'Hopital's rule. As soon as we see that, they're testing you on L'Hopital's rule. So that just means now we're going to take our derivative of these. So the derivative of the numerator would just be f prime. The derivative of our denominator is a 1. There is 0 chance now that we get 0 over 0, so this should give us our answer. So this is f of x. So if I want f prime of x, I really just take the derivative of those terms on the right-hand side. So the 1/3 would become a 0. This is really a fancy way of writing 2/9. So the derivative of 2/9 x would just be 2/9. The next one, I would get 6x over 3 cubed. And then it doesn't matter after that, right? Because when I get an x squared, then I'm going to get some sort of a coefficient for an x cubed. If I then evaluate this at the x value of 0, so if I now let my composite be a 0 here, then that would go away. That's going to drop out. That's going to drop out. Aren't we now simply left with 2/9? So 2/9 then ends up being that limit. Right? This is why they're clever. I give them a lot of credit. Like, here's a Taylor series, polynomial, Maclaurin series, all that, and then a L'Hopital's rule pops up. All right. All right, B. Write the first 3 non-zero terms in the general term. So the first 3 non-zero and the general term for an infinite series that represents this. So set that up. So hopefully we're getting to a point. This will be our 6th free response question on these, that we could understand what needs to be done there. This, since you're going to need to see it and you might not have it. So you have the function at the top, and then you're integrating that from 0 to 1. So this is f of x, and they want you to integrate that from 0 to 1, first 3 non-zero terms. Once we have that, then write the general term. One. All right, so hopefully we're just taking the first 3 terms in the function f that was at the top of the paper. You're just putting them within the integral. We're going to do our antiderivative. We're going to plug in the upper limit and then subtract our lower limit. So when we plug in the upper, you would get a 1/3. Plus, here the 2's would have canceled, so you would get a 1/9. When I plug in a 1 right here, I get a 1 in the numerator and a 9 and a 3 in my denominator for a 27. That's the upper limit plugged in. And when we throw in our lower limit, there are x's everywhere. The x is going to become a 0. Lower limit doesn't give you anything extra. So what we would end up with is this here. And we then want to come up with the general term that would give us those. Now, keep in mind, before you write the general term, when we come up here, if I were to put a sigma in front of this to determine what we're going to start at, we need to start our new one at whichever one this one would have started at. So think about what that would mean. Am I starting at 0 or am I going to start at a 1? So where did this one start at? So that if I plugged in that value, I start with a 1/3. If it's 0, the new one needs to start at 0. If it's 1, the new one needs to start at 1. All right, that's how we know where to start these in terms of making sure that we get our points. So do we all agree if I plug that in, that this one would have started at 0? All right, so the general term that you're going to come up with needs to make sure that if we were to write the sigma, which we don't necessarily need to do, but when n is a 0, you get 1/3, and then when n is a 1, you get 1/9, 1/27, so on and so forth. Okay. If you get it, you can do part C also, because C, I actually missed the time I keyed this up doing this real quick. See if you're better than me and didn't make this little mistake. All right, let's see what we got for B. The numerator is pretty easy, right? It's always a 1, so there's no real thought process there. And then we have 3, 9, 27. So we have 3 getting multiplied by itself over and over again. So we definitely have a 3 as the base. And then since we want to make sure that if n is a 0, that we start with a power of 1 right from the get-go, then we can't just have an n. It would have to be an n plus a 1. All right. So we got that. Good. Letter C, go down to letter C. It's asking you for the sum of the series that we just found in part C. Well, when we look at this, and again, they don't say find the sum of this geometric series. You would just have to understand, isn't this a geometric series? Are we multiplying by 1/3 over and over and over again? And then no, we have a formula for that. All right, a sub 1 over 1 minus an r. The reason we're finding all of them, it wants the sum of the series. So don't just add up these 3 terms that we just found right here. We want the sum of all of them. And that's this little guy right there. All right. So the first term is the 1/3. We have 1 minus our ratio. We are multiplying by 1/3 as well. So we have 1/3 divided by 2/3. So our sum, is 1/2. All right. All right. Then the last Taylor series, Maclaurin series, I might do another one when we get together. If you didn't hear, I am going to do something Sunday night, just as kind of a last refresher. We might do another one of these. This is like our 7th or 8th one of them, just so hopefully we got a pretty decent handle on them. But if I can find one that's interesting, that's a little different than what we've seen before, that might be one of the things we do on that night. This one to me is interesting and a little bit different. They freaked out on this one. This was just maybe 2 or 3 years ago. This question was on there. And again, it's just them being creative. All right. It doesn't look like any problem that we've done before, but it is the stuff that we have been doing. So we don't want to make this harder than it seems to be. So they start out by giving you a functional value at 0, the derivative value at 0, and then this is where people freaked out, trying to figure out what in the heck this means. All right, so we'll get to that. And then that's for all n values greater than or equal to a 1. So it says a function has a derivatives of all orders between a -1 to 1. The derivatives of f satisfy the conditions above. The Maclaurin series converges in this interval of convergence. So they're giving you the interval of convergence, so you don't have to worry about that question. And then all you're doing in A now is showing, they're giving you the answer. This is what it has to look like. And they want you to show that the first 4 non-zero terms in the Maclaurin series for f are this. And then you want to write the general term for it. Okay? So because we're going to write the first 4 terms and the general term, when we go to do this, you can actually use f of x and an equal to sign. Starts easy enough, right? We need our functional value, that's 0. However, that's not going to count as one of our first 4 terms, right? Because we wanted the first 4 non-zero terms, but that's our functional value. Then we now start with our whole little process here. Actually, let me just write the formula. So in a Taylor series, Maclaurin series, we would now want f prime to 0, x to the first, 1 factorial. And then we want the second derivative at 0, x squared, 2 factorial. Third derivative at 0, x cubed, 3 factorial. Then we probably need at least one more to get to the fourth non-zero term. And then we'll want to come up with whatever that general term is. So the trick here is, how do we get these values? The first one is easy. So if I ask you what is f primed of 0, don't mess that up. That's one of the things that they gave us at the top of the paper. F primed of 0 is a 1. So we're going to come down here. We know that this is a 1. So take a minute. We have a little bit. This is the main question I wanted you to see as part A. B and C are pretty reasonable. Like, we've done some of these. So A is the one, just because last year they all came back freaking out about this. See if you could get the second derivative at 0. How are we getting that? All right, and as a hint, if you get -1, you did it right. Okay, and then you're probably on the right pattern. You can continue on and get the next one. You sort of understand what needs to be done, but it's a -1 for that second derivative value. Okay, all right, let's jump in before we lose too much time. All right, we want the second derivative, right? This is what we need. So if I look at the way they're giving us to figure out what our derivatives are, so this right here, if I want this to be the second tick, f double prime, doesn't n here have to equal a 1? So that would ultimately get f to the second derivative value. So if n needs to be 1 here, it also needs to be 1 here and here. So what that really means is, and you need to show this somewhere. I don't want to move it, so you probably want to do this down here where they can see your work in part A. So you need to actually show what we did. The second derivative at 0 should have been when n is a 1. So you would put a -1, and then we want the first derivative value at 0. So then that would be the -1. We know the first derivative value at 0. That was given to us up here as a value of 1. And then we want to show that somewhere, probably underneath the work for A, so that they know that you did it. And then now we can replace this with a -1. Okay. And if you understand that, then hopefully we kind of understand how we're going to get the rest of these. So in the next one, if I want my third derivative, which we do, then this right here needs to be f to the triple primed. So n needs to be a 2, so that I get f to the 3. So then this n has to be a 2. So the third derivative value at 0 means n is a 2, so -2. And then I want the second derivative of 0 at 0 multiplied by that -2. The second derivative of 0 we just found, right? It was right here. That's a -1. So that one should give us a +2. All right, following that, now we can do 4 is when the n is a 3. You can kind of figure all that out. That was, what, 6, looks like. And then write the general term for that. See what we think. When you think you have the general term, let your n equal whatever you think it starts at and see if it actually produces what we want. Uh-oh. I'll be right back. Sorry, our puppy rang the I need to go to the bathroom bell. Don't want to risk that. All right.